Hello everyone. Yeah, my name is Atwine Sajias, and given such a mini assignment, I will take you through part 2, because part 1, you see, it is just a PDF kind of thing. So in the part 2 of this session of this paper, I'm told to implement a multi-threaded C program that stimulates a simple resource sharing scenario using a mutex and a semaphore. So instructions, we are told to imagine a shared resource represented by a counter, multiple threads, all that. Because I'm not reading it to the lecture, he knows what he said for us. So the requirements, we are told to implement a program that includes 3 threads: incrementer, decrementer, and the observer, I myself. The incrementer thread should, all that. So to start with, I think I can just give you a quick review of what a mutex means. A mutex could be a short form for a mutual exclusion, and it's a binary synchronization primitive that ensures only one thread can access a resource or a critical session at any given time, whereas a semaphore, it is also a binary synchronization primitive, but for it is just to control access to a pool of resources with a specified limit on concurrent access. So to not waste time, I think we shall go straight to the code. And the code itself, as you can see it, it has that hash include, that one will include the standard input output library, the hash include phthread.h. This is a new for us. So this one will include the POS IX thread library. This is just we are still on the library. It is just an execution model that exists independently from a programming language as well as a parallel execution model. For this one, it will just help me to control multiple different flows of work that overlap in time. So when I go to line 4 to define the num incrementers, to define, so for line 4, I'm trying to define a constant for the number of incrementer threads. Then line 5, define a constant for a number of decrementer threads. Then line 6, I'm defining a constant for the number of observer threads. When you go to line 8, here I'm defining a constant for the number of iterations each thread performs. So line 10, I have defined a global variable to represent the shared resource. Line 11, I'm defining the global mutex, which we say the mutex stands for mutual exclusion, to synchronize access to the shared resource. Line 13, I'm opening a function. This is a function to define the incrementer thread, where the int I on line 14 declares a local variable for the root index. Then line 15, for I equal to 0 I iterations, then I plus we call this one an increment. It will repeat iteration times and then acquire the mutex on line 16. Line 17, that is the increment of the counter. Line 18, uh, this will print the current value of the counter, and line 19 will release the mutex. So we shall return now, meaning we shall exit a thread. We shall exit this thread. So we shall open another function for the decrementer, where we shall open another function for the decrementer as we did above for the incrementer. Line 24. Yeah, I'm defining the decrementer thread function, where the int I, it is also a declare. I'm declaring a local variable for the loop index. Then for I equaling to 0, I iterations plus plus, I'm trying to repeat its iteration times like I did above. Then we acquire the mutex, the mutual exclusion, and decrement the counter on line 28. Then we shall print %d. This is C programming. I'm trying to print the current value of the counter and then release the mutex with a return now. Sorry for that. As I did above, uh, I'm opening another function on line 35. So I will define everything as I did above. Define the observer thread function on line 35. Then I initialize on line 36. Then declare the local variable for the loop index. Then on line 37, repeat the iteration times. Then print f line 39, print the current value of the count, and then release the mutex on line 40. Return out. I'm exiting that thread. Then after that, I'm calling the main function. The main function on line 45, line 46. I'm trying to define the main function. What is in the main function now? On line 46, I'm declaring an array of the thread variables for the incrementers. Doing the same, declare an array of the thread variables for the decrementers on line 47. Then line 48, I'm declaring an array of thread variables for the observers. Line 50, the per thread mutex initialize me that percentage and mutex now. Initializing now the mutual exclusive, the binary synchronization. Yeah, I'm bringing it up there. Then trying to declare the local variable for the loop index now within the main function. So for I, here where we have the increment, the first line on line 53, for each increment thread, this is a for loop. So for each increment thread, we'll create the thread and pass the incrementer function as the argument. Then for 57, for each decrementer thread, we'll create the thread and pass the decrementer function as the argument. So on line 61, it will do the same as above for each observer on line 61. Then 62, it will create the thread and pass the observer function as the argument. Then on line 65, for line 65, for each for each increment thread. Then here where we have line 66, here it will wait a bit for the thread to finish. We shall do the same for the decrementer waiting to finish and the observer waiting to finish. Then after, on line 77, we shall destroy the mutex after running. So let's go to our Ubuntu and explain whatever and run whatever we have been doing. So before that, what are we trying to do? There is something in the previous lecture where our beloved lecturer, Mr. Mutaganjiwa Vincent, taught us about the race condition. This is just brought about when you have a shared resource that is accessed by more than one process. Yeah, if not controlled, the output is unpredictable. So for this exercise, we are trying to first focus on the mutex, using the mutex, and then we can use the semaphore in the other video. Thank you. So to begin with, we shall put ls. So those are some of the directories that we have. So we shall first compile. Our C file by running gcc, then a space counter 1.c, then minus o counter 1. So before we have just been running and it has been storing it in an a.out. So for this case scenario, we shall create our own, our very own. We shall not wait for the computer to do everything for us. This time around, I have to instruct the computer to tell it what I want. So I want it to not to go to the a.out. No, I want to call something I know. So when we run this, we're expecting it to, when we run the counter, we're expecting it to so when we shall run this counter, we are expecting it to increment from 0 to 1,000. Then the observer will be able to see the 1,000 part alone, because this is the back end that you are not supposed to see. The observer will see the 1,000, then it will again decrement from 1,000 to 0. Like that. So the decrement now is back to 0. I think for the first exercise, this is all that was required. Thank you, everyone. We call it a day.